Session 3, as I mentioned, is all about fitting metalog distributions to data. Typically empirical data. It could also be simulated data, but whatever it is, it's data. And as a reminder from session 1, we went over this example of the catch and release fish records for the years 2010 through 2014 of 3,474 steelhead trout that had gone up the Steelhead River and that were caught and released in the Babine River in northern British Columbia. And the plot of the data looks like this. And if you try to fit that with like a log normal distribution, that's the green, you actually come pretty close. The plot of this data is all the yellow and the gray. But what we noticed was, there's a fact about steelhead life cycle, which is that they come up the river to spawn. They live most of their lives in the ocean, but they come up the river to spawn, and they can do so multiple times. They're not like salmon. They don't die after they spawn. They can go up and spawn and then go back to the ocean again. And first time they come up, they tend to be smaller, 1 salt fish. Second time they come up, they tend to be larger, 2 salt fish. And basically, fish biologists really don't know how many of each kind are in the river or what are the relative population sizes. If you look at the histogram of that data, you can see it here on this chart, as well as the log normal distribution, which is probably what they would have either, most fish biologists would have either used that or I can't think of the name of it. There are a whole bunch of distributions that look like the log normal that they might have used, but that masks the actual shape of the data. And if you do this with a 2-term log metalog, it looks like that: a 4-term, 6-term, 8-term, 10-term. All of a sudden, you end up with a shape of the data with a probability distribution that matches the shape of the data and that maybe gives you information here about the relative population of 1 salt versus 2 salt fish, as well as the population sizes. Okay. So, and not just the population sizes, but also the weight, which is the 1 salt fish tend to be more than 4 to 6, 7 pounds, and the 2 salt fish tend to be 8, 10 pounds and over. And there are also a very few 3 or 4 salt fish that get up to 20, 30. I think the largest steelhead ever caught and released on record was over 40 pounds. So the idea here is what can be learned from the data and how do you fit that data, how do you fit a metalog to that data without overfitting or underfitting. I'd like to do a couple more key examples here before we move into the Excel workshop. This is the DMS data is one of the most famous data sets in all of the world of finance. It's been analyzed for years and years and years by many researchers, including Harry Markowitz, the Nobel laureate, who published a whole analysis of it in his 2014 book, Risk and Return Analysis, Volume 1. What this data is the annual return for the stock market in 19 countries for whom that return was stable and somehow measurable over the years 1900 through 2000. So for each of these 19 countries, there are 101 data points, and you can see the countries listed there. Now, the reason this data set is so important is because it gives you an overall sense of what's the skewness and kurtosis, as well as the mean and variances of stock market returns. And if you take all this data and put it together in, Harry Markowitz calls it the ensemble. If you take all this data and put it together, you end up with whatever it is, 1,919 data points, something like that. And if you look at that compared to the chart we've discussed many times about the standardized skewness and the standardized kurtosis being heavy tails. Heavy-tailed distributions go down on this diagram. Extremely skewed distributions move from the left-hand axis to the right on this diagram, and anything on the left-hand axis is a symmetric distribution. you can see where this data lies. It's a slightly skewed data set. The returns on stock market data is slightly skewed for many data sets, but for many stock market data sets, it's more sort of, it has not too much skewness. Now, for some data sets, it has lots of skewness, particularly if you try to measure options or something like that. But for now, let's just stick with the returns on the market data. But one of the most famous findings in finance, and this was again amplified by Harry Markowitz as well as others, is that there's a large amount of kurtosis. These are relatively fat-tailed distributions that you need to model stock market return data. And in fact, this is the student t-distribution with 5 degrees of freedom here. This is the student t-distribution with 4 degrees of freedom. You can see that the stock market data falls between 4 and 5 degrees of freedom. And if you ever spent much time looking at the student t-distributions, you would find that between 4 and 5 degrees of freedom are quite fat tails. And in fact, the only ones that have fatter tails are like 2 degrees of freedom or 1, which is the Cauchy distribution, which is so extreme that it doesn't have any moments at all. But anyway, that's where the data lies on that diagram. Now, Harry Markowitz has spent a considerable amount of time talking about the Pearson distributions, which we talked about also in session 1 as being the sort of the benchmark against which other flexible distributions are measured. And if you were to take that data, which is measured which is plotted with the gray points on the left-hand diagram here as a CDF, and you're to do the best fit that you could with a normal distribution, you can see that the normal distribution is too fat in the middle and doesn't have fat enough tails. But it's not a bad fit overall, it's just not great. And Harry went through all the Pearson distributions and determined that the Pearson type 4 distribution, which is such a difficult distribution to use that you can hardly even write its equation, but he did find that a Pearson type 4 distribution was the best possible fit to that data compared to compared to the normal, the beta, the student T's, anything else you can mention. This particular Pearson type 4 distribution was the best. And famously, Harry showed in various papers, along with some well-known colleagues of his, he showed that if you started off from a Bayesian perspective and without knowing this analysis, and you said, how likely is it that the normal distribution could have generated this data versus the particular Pearson 4 distribution, which he found particular parameters for it, versus the Pearson 4 distribution, he famously came up with the conclusion that no matter, suppose you started with your probability of 50-50, it's 50-50 the Pearson 4 versus the normal. Well, suppose you started that as your prior distribution. Harry famously showed that you would have to reduce your probability of it being the normal distribution that was the source of the data by 67.7 orders of magnitude compared to the Pearson 4 distribution, which is an extraordinary finding and is published in his book. So Harry at Sam's, Sam made this nice introduction to Harry, and Harry wanted to learn about the Metalog distributions, and before going to see him, I said, well, what data set can I apply the Metalogs to? And he said, well, this is the data set. I'd like to see an application of this data set. So I went through the Metalog family of distributions and found a Metalog distribution that that basically meets this data better than the Pearson 4, in fact, better than any possible Pearson distribution. And in fact, the Metalog is 1.74 orders of magnitude more likely to have generated the data than the best of the Pearson 4 distributions. And so we had a chance, Sam and I, this led to an invitation, again facilitated by Sam, to go visit Harry Markowitz in San Diego. And by the way, he's wonderful, energetic, intellectually curious human being, still at a, at quite a, well, let's say he's a lot older than we are at this point. But Harry eventually asked me for his pen. I said, well, what do you want my pen for? And he signed this sheet. He said, "Hallelujah, I believe Harry Markowitz." So all of a sudden, the Metalogs actually have an endorsement, a literal endorsement from Harry, which was quite cool and quite fun. But again, the point here is, if you have a set of data, the Metalogs are far more flexible than any of the Pearson distributions, and they're far easier to fit to that data than any of the Pearson distributions. So, it took me about 10 minutes to do this fit, or maybe even 5 minutes. Whereas I imagine Harry and any of his colleagues and going through all of the Pearson distributions to find a best fit Pearson distribution, unless they had designed some specialized software to do that automatically, it might have taken them months. I mean, it's not trivial, all these Pearson distributions to fit two data sets, because you got to do maximum likelihood estimation. You got to do all of the things where all of those distributions go wrong or crash the software, or don't have, or where the nonlinear optimization converges to something that's a local minimum versus a global minimum, and so forth. So anyway, that's one story. Another one that I'd like to tell you, this also came from finance, and one of the people, when he first saw Metalogs, was the director of research of one of the world's largest both investment banks, consumer banks, and then also advisors of high net worth individuals. And he was the head of research that informs all the people that are working with and he writes papers all the time about various trends in the stock market. And he gave me 18 data sets, one of which was returns on gold, and said, what would the Metalogs see in these data sets? Because he's used to modeling these, again, with Pearson distributions, and particularly with a normal distribution or a Johnson distribution, which has 4 parameters and can be slightly skewed or whatever. But anyway, he gave me these returns, and there they all are these are quarterly returns on the price of gold from March 31st, that's Q1 of 1998, through the September 30th of 2019. And there they all are. These are percentage returns if you invested at the beginning of the quarter and then sold at the end of the quarter. And this is the histogram of the actual data. Now, what do we see? And this is of some importance for the discussion we're about to have. If you were to fit this to a normal distribution, you'd get something like that. And this is what he is used to doing, right? And he is quite used to fitting all of his data to normal distributions and saying, well, okay, that data, it looks actually a little fatter than normal, but normal probably isn't too bad for rough purposes, is what he was used to doing. And when we went through the Metalogs, we saw, well, if you use a 2-term Metalog, that would be a logistic distribution exactly. That actually is not as good a fit to the data as the normal, because the histogram is fatter than what the logistic shows. If you use the 3-term Metalog, you would end up with you end up capturing the skewness that's in the histogram, but still not the fatness in the center. If you go to the 4-term Metalog, now you've got something that's capturing both the skewness and some of the fatness that you see in the center. If you go to the 5-term Metalog, that thing is now, the 5-term is now beginning to recognize that there's that there may be, a high peak over there on that right side, which is different than the center of the distribution. The 6-term Metalog is actually showing a binomial, a bimodal shape. And you go, well, gee, that's interesting, but I'm not seeing that. I'm seeing the right mode in the data, but I'm not seeing the left mode in the data. And then if you go to the 7-term Metalog, that left-hand peak is even sharper, and if you go to the 8-term Metalog, there you are. And you say, well, that's probably a better fit than the normal. Why do we have that peak over there on the left? Well, it turns out that that particular histogram is not capturing something that the Metalog is seeing. Now, what would that be? Well, if you redid the histogram to give it a little bit more definition, if you narrow the bend width a little bit, all of a sudden you're seeing that peak. And there it is, right? So the key point here is that, well, there are several key points. First of all, you need to look at multiple Metalog distributions, not just one or two. And the nice thing about the Metalog family, I'm going to show you a tool in just a second called the Metalog panel, where you can look at the shapes all at once and sort of begin to get some visual indication of where the shapes are stable, where they're not stable, how they work together, how they don't. What are feasibility considerations and so forth. But so one point is you need to look at a lot of shapes in order to determine what's the best best Metalog. And it also depends a lot on context. What do you know? Because what do you know about the world? Because when this gentleman saw this bimodality, he was frankly shocked. He had never seen bimodality in the price of gold. And he immediately started talking about, of course, what's his field of expertise. He said, I'm going to have to go back and look at that data. I wonder if it actually is bimodal. I wonder if we should check and look at monthly returns rather than quarterly returns, or annual returns, or returns from different time periods, and so forth. So that's part of where his mind went with this, is like, if this is a real effect, I need to be writing articles on this, because this could affect the design of derivative instruments. People could, if you really knew that it was more likely to be higher or lower than zero and not really at zero, and less likely to be at zero, that would affect the design of options. And the first company that did this could maybe make millions of dollars based on designing instruments to take advantage of this behavior, if it were proven to be a stable behavior. And then the next place his mind went was, well, I wonder why this might be happening. And he said, I'm going to go back and look at all this data, and I'm going to find out when the central banks were buying and selling gold. Because he says the central banks have a large herd instinct, and they tend to all buy and sell gold at the same time. That is, when they decide everything except gold is more risky, or that everything except gold, or that gold is, less interesting because everything else is a better investment. But whatever, and so he went off and started embarking on an aspect of research to persuade himself in his own mind that he could use central banks' likely behavior as a leading indicator of what was going to be happening to the price of gold in a given quarter. All right, so I've made that a relatively complete story, but it's important for a number of reasons. One is, to get the shape right, you need to look at multiple Metalogs. Two is the Metalogs are more stable than a histogram representation, which depends critically on bin width and starting point for the histogram. And then thirdly, context, what you know about the situation, what you know about your data, likely explanations for what's high, what's low, and why, and what might come into effect in terms of future forecasting is really critical. So this becomes a tool for experts to learn more about their field of expertise, and maybe even in a deeper way that they can then communicate to other experts, and then use basically to do their business better or more effectively.